taken the previous class, air traffic management, but if you didn't, this will be very new and would be interesting. I will not go through detailed equations like the previous class, but I'll just tell you how to calculate the great circle distance. So the coordinate system that you guys would be a lot more familiar with is this XY coordinate system. This is called Cartesian. I'm not sure there are two S's or one S, Cartesian coordinate system, because it was invented by this guy, Descartes of France, who is famous for a philosopher, and his most famous sentence is "I exist because I think." 좀 나는 생각한다, 보로 존재한다. 그 말을 했던 그 데카르트가 그런 쓸데없는 말만 한 게 아니라 굉장히 쓸데있는 짓을 한 거죠. So maybe this is like a 1,000,000 times more important contribution of him, of this coordinate system, x and y. However, the problem with, if you like look near your area locally, it's fine, but if you look at the Earth is almost a perfect round ball. It's a sphere, and it's basically impossible to express any position using the simple xy coordinate. So for describing a position on Earth, people invented this kind of a spherical coordinate system a long time ago, before the airplanes, because they had to navigate their ships around the world across the ocean. So if you look at this picture, this is the Earth, and this is the rotational axis. So here, this is the North Pole, and this is the South Pole. Now, if you cut the center of the sphere, if you cut it along this plane, which is, this is the rotational axis, perpendicular to the rotational axis, there will be a big circle, like this. So this line is called the equator. And then, if you cut parallel to this surface, like this, you will get lines like this. So those lines are called parallels. So these are, if you think about the slice, it's like cutting the apple like this, and this circle is the largest at the equator, and it gets smaller if you go north towards the North Pole, or if you go south toward the South Pole. At the North Pole or at the South Pole, this is 0. It's just the 1 point. Now, let's cut the Earth along the rotational axis. So then, this is the equator, and this is the axis, North Pole and the South Pole. Now, these parallels can be expressed by, if there is a parallel here, the degree, the angle from the equator. So 0 degree would be the equator itself, plus 90 degree, that would be the North Pole, and minus 90 degree, that will be the South Pole. So this angle here is called the latitude. So as the latitude goes up, the 0 degree latitude is the equator itself, 10, 20, up to 90. 90, again, it's the 1 point. So here, you can see, these are the latitudes. The equator, latitude 10 degrees, a slightly smaller circle, latitude 20 degrees, gets smaller, 30 degrees, 40 degrees. And most of the famous places, including South Korea or Europe, United States, they are kind of located somewhere around here, like between 30 and 40. That's called the mid-latitude place. And the reason why they have the sort of the best weather for people to live. And then above 50, 60, it gets really cold. So that was the latitude. Now, slightly erase this. Now again, think about the cut that goes through the rotational axis. Then that's like your regular, how your mom cuts your apple, like this. So in that case, however you cut, it's gonna be the big circle. So this is the equator. So whether you cut like this, or you cut like this, it's gonna be the same size circle. So these cuts, these circles, are called meridians. This S is for plural. 단수 복수할 때 S죠. So this is called meridian. And unlike the parallels, for the parallel, there could be basically three intuitive references. It could be either the equator, or the North Pole, or the South Pole. So if you, however, the meridians, it's all the same. There's no kind of a intuitive reference. So people had to just make a arbitrary meridian to be 0. So that meridian is called the prime meridian. And the time, I'm not sure, it's very likely to be some 17th or 18th century when the mostly world evolved around Europe and people made the measurement and fixed the numbers. The UK was the superpower at that time, more like called Great Britain. So they just made the line going through their Greenwich Observatory to be the 0 meridian. So it's still that 0 meridian. So this one, let's say this is the one, 0 meridian, prime meridian. And if you go towards the east, it's plus. If you go towards the west, it's minus. So east, west. So any point here, let's say this point here, with the mouse, this point, in terms of north and south, this is on the 30-degree latitude. And in terms of east and west, this is 30-degree longitude. So now this is the Earth. If you look from above the North Pole, this is a 0 prime meridian, and then this angle lambda is called the longitude. So towards the east, this is plus. So if we look near South Korea, you can see these numbers. It's about 33-ish north latitude up to 38 north in terms of latitude, and in terms of longitude, it's 125, 130-ish towards the east from the Prime Meridian. And the 38 north, that was the border between South Korea and North Korea before the Korean War. And that was just basically the average of the two latitudes, north and south end. So the latitude of the Mount Baekdu and maybe the latitude of Jeju Island. The middle one was 38. And the Russians and the Americans just arbitrarily marked a line and decided to govern the country north by Russians and south by the Americans. And then after the war, the DMZ line is slightly different. So let's look at the Google Earth. It's more fun here. Now, near the North Pole, let's go to somewhere in Alaska. So this part, this is Alaska of US. Actually, you can see it's about 60, let's see, 70, 65, 60 degree north and a little bit above. So if we come down here towards the equator, these are not rectangle. These are basically trapezoids. As you go up, it gets slightly shorter, but they look more like a rectangle. However, if you get closer to the North Pole, now it's pretty obvious that it's shorter at the upper side. Now, if you actually go to the North Pole, it becomes a triangle because it's all converges here. And if you go to Korea, right here. So you are at this point. Let's say latitude 37, longitude 126. Maybe this is close to the Incheon International Airport. Now, from this coordinate, if your latitude increase, you are going directly north. If your latitude decrease, you're going down. If your longitude increase, you go east. If your longitude decrease, you go west. So, in some sense, the longitude is similar to your x-axis, and the latitude is similar to your y-axis, but they're not identical. You can just think it's similar. Okay, so the next one is the shortest distance. Now, if you look at, maybe go to the Korean Air website and look at the cities that Korean Air flight goes from the Incheon airport, you will see lines, and they are all curved lines. You would never see a straight line. And you might have wondered why they use straight line. the straight line is shorter. And let's say from here, Korea, to here, somewhere in the US, let's say San Francisco. This is kind of the map of the world that you're familiar with. And compared to this route and this route, which one's going to be shorter, actually? The red line is actually shorter. And that's pretty obvious if you get the model of the globe and if you rotate it around. But on this map, it's very counterintuitive. So let's look at the Earth again. So let's measure distance. Here. So, because this is a distant measure, it's always a straight line, I mean the shortest path. And if we kind of look in this angle, it looks like it's curving upward and coming down. But if we actually rotate it like this, it's more like a straight line. So that's why you can see for the kind of mid-latitude locations, it's slightly going north and coming back down is the shortest path. So this path, if we assume the Earth is a perfect sphere, is called the Great Circle distance. In reality, the Earth is not a perfect square. It's a slightly bigger in the equator. However, for our purpose, we're going to assume it's a perfect square. Now you can also see that why sometimes going over the North Pole is even shorter. Let's say we are going to not the San Francisco, but New York City. Now you get very close to the North Pole. So let's draw one more line. Doesn't really work. So let's go back to this map. So from, San Francisco to Incheon, it takes about 12 hours. If you fly from San Francisco to New York, it takes 5 hours. But if you fly from New York to Incheon directly, it takes like 13 and a half or 14 hours. So in that kind of a map, it looks like this, but in reality, it's more like this. So this distance and this distance, there's not a really big difference. And if you are actually going to somewhere in Europe, like London, again, the route will be like this. You fly over most of the Russia. So in the old days, during the Cold War era, when the Russia and Eastern Europe, they are the communist countries, and the Western Europe, South Korea, and the U.S., they are the democratic countries. They're like preparing to have a war. The Russia didn't allow this flight to go over their territory, so the flights used to be longer. Now, after everybody opened up their sky, and they're charging money for that. You better, it's a good business. So, I mean, if this talk between North Korea and South Korea goes well, even before the connecting the train or any other thing, North Korea might just open up their sky and charge money. Like you can see, even the shortest route to San Francisco, it goes through the Pyongyang FIR that we've seen before. That way, we can save like time, 20 minutes of flight, and also fuel. And North Korea can make money, so it's a win-win. Unless they use that money to develop more nuclear weapons. I mean, as far as they don't use the money in some bad way, it's good for both parties. The people flying can save money and time, and the North Koreans can make money. Okay, so now how do you calculate the shortest distance? So there are 2 points on the Earth, and basically, if you cut the Earth that go through these 2 points and the center of the Earth, so it's not the best picture. Let's say you cut it in this kind of a plane. Then if you connect to the center of the Earth, from the center of the Earth to any point on the surface, the distance is the same. It's going to be the radius of the Earth. So all that you need to find out is the angle between the 2 points. So the shortest distance is just the radius of the Earth multiplied by the angle between the 2 points. And for these points, let's say first point, we express this using latitude and longitude. So latitude, longitude. Like this. Then the formula to calculate the distance is r, the radius of the Earth, times r cosine of cosine phi 1, cosine phi 2, plus sine phi 1, sine phi 2. It's like this, but there's one more term here, that is cosine lambda 1 minus lambda 2. So, a little more complicated than your Pythagorean theorem. I mean, if it's like not if the latitude is not very high around Korea, we saw this is similar to rectangle. So you might think this distance is going to be similar to A, B, C. So C squared, A squared plus B squared. That's what you might intuitively think. So this will give you a approximate distance as far as you don't, the area is small and the location is not too up north or south. But near the North Pole or near the South Pole, it's gonna just completely fail. So actually, there are a group of people who still believes Earth is still flat. And if you have to deal with the circular model of the Earth, and especially if you have to deal with the, not even a circle, it's a ellipsoid, which is a rotated ellipse, then the math is so complicated, you might wish I would rather have a flat Earth. So that's it for the coordinate system. You guys, as an engineer, mostly engineers in the aerospace engineering department, must have seen bad units. The unit is this really irritating problem. So this is the, let's say, light side. And this is the dark side. Or we can say this is good, or this is bad. Here we use meters. In the dark side, they use feet. We use kilogram. The dark side, you don't even know what they use. Now, in the dark side, they use pound. And here, we use Newton. The dark side unit for the mass is slug. Might have seen this in some class. Things like that. It's really bad. And they have all these weird units as ounce and yard. It goes on and on and on. However, unfortunately, the aviation is dominated by the United States, who use the dark side of the unit. So we still have to learn some of this unit. However, for the aviation, we have to learn some more units in addition to the bad units. There are new units that will be introduced. That's most notably for the distance, it's nautical miles. So 1 nautical mile is exactly 1852 meters. Weird number. Now, Americans, the bad guys, use mile. And this is different. 1 mile is 1.609 whatever forever meters. So you shouldn't be confused with the miles and the nautical mile. Sometimes, to make things clear, this mile is called the, with an S, statute mile. Now, where this weird one comes from, so to understand the nautical mile unit, we have to learn a little bit about the degrees. That you all know. So we that a full circle is 360 degrees. And here, there's a interesting format, 123 degree, 45 minutes, 19 seconds. So for the degrees, traditionally, they use the degree, minute, second format a lot. So this is called the Dmx format. And just like the time, in the time we still use minute and second. So 60 minutes is 1 degree and 60 seconds is 1 minute. So 3600 seconds is 1 degree. So degree is like hour, and minute is minute, second is second. So this is actually a rather commonly used format in the maps and in aviation. So it's called the Dmx format. Now, to convert this to just degrees, we can do this by the 45 minute is 45 over 60, and the 19 seconds is 19 3600. So if we do this, we will get just everything in degrees. That's 123.7533 goes forever. So if it's just expressed in degrees with the decimal points, this called the decimal degrees. Because if you have to do any sort of calculation, we've seen this cosines and sines of degree, you have to use at least the decimal degrees, and usually your computer code or the calculator, you have to convert this to radians. So divided this by 180, multiplied pi. The radian is the standard good guys unit for the degrees, and that's the standard. Any of the computer code, C language, Java language, Android, MATLAB, everything is based on radian. There's sometimes they provide special functions so that you can just use degrees, but it's the radian is always the standard. So if you have just a simple calculator that takes radian, then from the Dmx format, we'll have to convert to the decimal degree and then to the radians to do that sine cosine calculation. Here, now, again, this is the Earth, this is equator. Now let's say you don't change in your longitude is fixed, and your latitude only changes. Now the distance you go up north with 1 degree of latitude change, that will be the same anywhere. It's going to be the same at the equator, it's going to be the same at like a 30-degree latitude. It's just the radius of the Earth multiplied by your change in your latitude. Now, for your change in 1 minute latitude, 1 over 60 degree, that distance is actually about 1852 meters. So that's where this 1 nautical mile comes from. Let's see. Here. So actually, I set up the Google Earth to express the degrees in degree minute second format. So here, 37 degrees 30 minutes, 37 degrees 42 minutes. So from here to here, there's 12-minute difference. And then you can very quickly see the distance here is just 12 nautical miles. So with the degree minute second DMS format of the angles, and with the nautical mile unit of the distance, it's very easy to go back and forth. That's why it's used. So 1 nautical mile is 1852 meters. Now, this is because the Earth is not a complete sphere, that 1 minute of change, the distance is slightly different between the